At that time, do we have Zoom
Yeah.
recording?
That's up and functional.
Okay, so the Zoom session's live. We have folks logged in?
Yep.
Okay. I'd like to start off with our discussion, continue our discussion with generating electricity. And all of you should have a Gen Con right next to you. Go ahead and get that out and get it plugged in. You want to have it set up so that you've got the leads coming out to alligator clips. And I'd like everybody try to connect that up to a light bulb to get it to light. Go ahead and do that now. Does everybody have it connected up? Colton, could you help anyone that's having difficulty connecting up the leads? Okay, so here's a question. Does it light no matter which way you turn the handle? You can turn the candle clockwise or counterclockwise. Does it light both ways? What do you think is different when you turn the crank one way or the other? Any thoughts about what could be different?
It could just be, but it seems like it's farther when I do it one direction.
You've got
It's your imagination.
one person online says the direction of electricity.
Yeah, it'll be at the direction of electricity. Who is that?
Ashley Wheatley.
Okay. Yeah, what'll happen is you'll change the direction of electricity. These are DC motors in the noses of these Gen Cons, and so they'll output direct current. And whether or not you turn it clockwise or counterclockwise will just change the direction of the electricity. And if you see it brighter one way or the other, that probably means you're cranking faster naturally one way as opposed to the other. Now, what I want you to do is to try it, just disconnect one of the leads and try to compare how easy it is to turn the crank with a lead connected or with a lead disconnected. Is it a lot easier to turn the crank if you're not having it connected up to both leads?
Yeah.
Okay, could someone tell me why that might be the case? Why would it be so much easier to turn the crank if you don't have a complete circuit? Mr. Anderson?
Again, it'd be different because it provides more magnetic resistance.
Okay, there's more resistance to it, and you use the term magnetic?
Yeah.
Well, that's actually, well, not precise, it's fairly safe, in that it takes energy to make electricity. In that as soon as you have electricity going through the coils, through the wires, those coils within the generator act like a magnet that'll be either repelled or attracted by the permanent magnets in that generator. So basically, if you don't have a complete circuit, you're not having charge move. You're not having electricity. There's not a complete circuit. And so it's going to be a whole lot easier to turn the crank because you're not having charge move, and that's not making all the coils in the generator magnetic. And then once that happens, you're going to get opposition. And the more load you have, well, the more opposition you're going to get. And something I think is common experience for a lot of folks, but it might not be. If you've ever worked in like a machine shop or a wood shop where you've got like a table saw or some sort of, usually it's saws that you notice this the most, like a table saw, a chop saw, maybe a skill saw even, where when you turn it on, the lights might dim a little bit because it's connected to the same circuit as your lights in many cases. Has anyone noticed that the lights will tend to dim briefly once you turn a saw on? But it's only when you're turning it on. And if you're dealing in a situation where a shop where, yeah, you're not getting the best, you don't have the best wiring, if you like do a a rip cut. Like you got a table saw and you're going to do a rip cut. That's a huge load on the table saw, meaning you're cutting through a lot of wood and the speed of the blade is going to slow down. And you might notice the lights dim and you can definitely hear the motor trying to work a little bit harder. What's happening is if you have a table saw or any saw just spinning freely, well, it takes a lot of electricity to get it up and going. And so you'll notice a draw in the other circuits. But once it's freely spinning, it's drawing very little electricity. And one way of thinking of that is that while it's spinning, it's acting like a generator as well, producing current to as well as drawing current. And since it's producing current, the total amount of electricity needed to run the thing is a lot less. And so you're not going to see the lights dim if a saw is spinning without any sort of load on it. But as soon as you put a load on it and it starts to slow down, it's not generating as much electricity. So it's going to have to draw more current from your household wiring. And so this is one way of thinking about how motors work, is they're always acting like generators as well. And if they're just going without much of a load on them, they're actually generating electricity to the point where the net draw is very little. So the the amount of current something draws does not really depend on the speed of the axle that's spinning. It has to do with sort of load is on it, because as soon as there's a load, it'll start to slow down and it's not going to generate as much power, and you'll see a difference in what it draws. So kind of another way of thinking about how shop equipment works. Was there a question?
I think it was just a hot mic.
Okay. So that's generating power. And there's one demo that I meant to do a bit earlier before I started talking about the speakers, but I just forgot, so I think I'd interject it now. I have a light bulb here. It's an old style light bulb with basically a carbon filament. And this one I know doesn't really show up well on camera.
Yeah.
But if I can power it with either 120 volts DC or 120 volts AC. And I want you to look closely. For those of you in the room, can you see a difference in the brightness? So here is DC. Here is AC. See any difference? AC, DC. No, there really isn't. Because you have the same amount of average current in each case, and so the brightness is going to be about the same. Is there any way to tell whether or not we have AC or DC current going through a light bulb just by looking at it, or is there some sort of experiment we might be able to do? Can anyone think of something? And for a clue, think back to how a speaker works. Do you remember you had the speaker on Friday with basically the cardboard box? We found out that, in fact, hey, Braden, why don't we get the cardboard box out again, because it never really worked well.
Okay.
We found out that it was the power strip on this table that was giving us not consistent enough power to run the amplifier.
Oh.
And as soon as we plugged it into something else, it worked great. But anyone? Any thoughts of how to tell whether we have AC power or DC power? Okay, that was kind of a long shot. But I've got a magnet here, a pretty strong one. I want folks to watch the filament closely. And you see what happened to the filament when I brought the magnet close? It's pushed. Which way is it pushed? Can you tell in the back?
Outward.
By outward, what do you mean? No, both filaments are pushed, one more than the other. The one that's closest to the magnet is pushed more, but both are pushed to your right. Can you see that?
Away from the magnet.
Yes, away from the magnet.
Can you also show on the left side? Like,
I don't think it's going to show up well.
No, it's too bright. It doesn't work well on the camera.
Yeah, I think we tried this before. It doesn't work well.
Yeah.
Okay, but watch what happens if I turn the magnet around. Now it's being pulled. So because the filament is looped, it's producing a magnetic field that's either in this direction or this direction. And that means if I bring the magnet in like this, with either a north pole on this side or a south pole on this side, it's either going to push the filaments away or pull them towards it. So the filaments are either pulled or pushed, depending on which way I have the magnet. Is everybody in class seeing that? Okay, now what do you think will happen if I put AC power on? Any predictions? And for those of you who are remote, you can go ahead and make a prediction based on my description of what happened. What might happen if I had this on AC power and I bring a magnet close?
One person said from Jim, no change.
No change. Who is that?
Jim Dinma,
Miss Ogbonna?
Obama? Okay.
and then Ivy Sackett said opposite, as well as Shelby Reynolds.
Opposite. What do they mean by opposite? Can one of you just speak up? What do you mean by opposite?
You get the read?
Yeah.
So in the first case, when you put the magnet close, it went away from you, I think. Is that right? Or to the right or something?
Yeah, it was either pulled towards the magnet or pushed away, depending on which way I pointed the magnet.
So I think that it's going to be the opposite with the with the same end that you would have put towards the first. I think it would go the opposite way that it went.
Why opposite?
I don't have a good explanation.
Okay. You remember that what's going on here is that the filament is behaving like a magnet because you have electricity going through it. I've got two loops here, and so it's producing a magnetic field either in this direction or in this direction, one or the other. I don't know which. I'd have to actually find a magnet that was labeled north or south to be able to tell the difference. But it's either going to be pushed away from the magnet or pulled with direct current. Now, remember with the speaker, when we sent an alternating current through, when it changed direction, well, let's just do it. Now it's on AC power.
It's vibrating.
Yes.
oscillating.
It's moving back and forth 60 times a second. And it really doesn't matter which end I bring close, it's always going to vibrate that way. And you'll see more vibration whatever filament is closer. Is everybody seeing that in class okay? Again, that's not going to show up online very well. But if the magnetic field is in this direction, see if I've got a north field, a north end of a magnet right here. If the magnetic field from the filament is in this direction towards the north pole, that's going to push the filament away. If the magnetic field if the magnetic field from the filament is in this direction, and I've got a north end of a magnet here, it's going to be pulled. But if we switch the direction of current, we switch the direction of the magnetic field. If the current's going through the loops this way, we're going to get a magnetic field in that direction. If the current's going the other way, we're going to get a magnetic field in this direction. With the current switching direction 60 times a second, the magnetic field is to the right, then the left, to the right, to the left, switching direction 60 times a second. So whether or not it's pulled or pushed away from the magnet will change every 60th of a second, so it vibrates. And that's how a speaker works. You send a changing electric current into a loop of wire, so it's pulled towards the magnet, pushed away, then pulled and pushed, and the frequency that it's pulled and pushed is the frequency of the signal. And by sending multiple signals in with different frequencies, you can get these wire loop and whatever it's attached to, a membrane, the speaker, whatever's moving, it will then vibrate at that frequency. And so, Brayden, can I borrow your? Yeah. My phone is on its last legs for battery, and I just noticed right before class. So we're going to use Brayden's phone. So go ahead and make sure that you got some music going.
To get out of the case in order to get the office light.
Can you
Yes,
still
that
see
would have
Victoria?
been useful
Can
earlier.
you still see?
Okay, I'm gonna adjust the volume here, so go ahead and pull your volume all the way up. Okay, you got it going?
Yep.
Okay, so. So not a bad speaker. Not a great speaker, but still it works. So, thanks. Yeah, I'll need that again later. Okay, we do something else. Okay. But that's again, kind of what's going on in the speaker. Now, we can also generate electricity using this idea. We saw the little hand crank generators. I have a tube here where I have little light emitting diodes on the tube. And if I drop the magnet through the tube, well, the moving magnet should create electricity in each of these coils. You see the light up? Is that showing up okay, or do we need to turn the lights?
Very well, we'll need to.
Okay, go ahead and do the lights. But can everybody in the classroom see the lights turn on and off?
There we go.
Is that showing up?
Oh, yeah.
Okay, these are again the bicolor LEDs. They turn green if electricity goes through the diode one way, and they turn red if the electricity goes the other direction. Now, if I have the magnet right in a coil, nothing. There has to be motion. If I move the coil instead of the magnet really wasn't moving much there. It was the coil moving back and forth. We get electricity. And if I hold the coil still and have the magnet moving, we get the same electricity. And you can see that it switches direction. This is called Lenz's law. And if the magnetic field is getting stronger near a coil, you're going to create electricity. Electricity is going to arise in that coil to produce a magnetic field that will oppose that increase. So if you've got a magnetic field to the right that's increasing in strength, that's going to induce currents to produce a magnetic field to the left. Now, if you have a magnetic field to the right and it's getting weaker, say with the magnet moving farther away, you're going to create currents to produce a magnetic field that's also to the right to oppose that decrease. So you're going to get a magnetic field from the magnet that's pretty much always in the same direction where the coil is. But if it's increasing in strength, you'll get currents created in one direction. And if it's decreasing in strength, like when the magnet's moving away, you're going to create currents in the other direction. So that's why the current changes direction. And that means that, well, those currents that are produced, if the magnet's getting closer, it's like creating a magnet that's got the opposite pole, and that will tend to push the moving magnet away. But once that magnet passes through the coil, the currents produce a magnetic field in the same direction. So it's like producing a magnet that's going to try to attract it back towards the coil. So you always get a current produced in such a way to oppose the change in magnetic flux or the change in the strength of the magnetic field. So let's go ahead and turn the lights back on. Now, if you look at the magnet, and you can probably see, even though you don't see the lights turning on, you can tell that the magnet is slowed as it goes through each of those coils. Can you all tell that? That's because it takes energy to make electricity, so it's like taking energy from its motion. This is like the Gen Cons. When you turn the crank, you found that you had more resistance if you had a complete circuit. But also, you can think of the currents in these coils producing their own magnetic fields that push and pull on the magnet as it moves through. Pushing it away as the magnet gets close, and then pulling it back as the magnet moves farther away. And this is how the brakes in the hybrid cars work. And then normally you have electricity from batteries going into the motor, and that runs the drivetrain, that spins the wheels. But when you hit the brakes, well, it basically changes the role of the electric motor in the car. It's no longer taking electricity from the batteries. What it's doing is that the drive wheels are then flipping the motor coils so that it acts like a generator, producing electricity. And you know that causes resistance. That'll take energy away from the motion of the car and then store it back in the batteries. So basically it turns the motor of the pirate car into a generator when you hit the brakes.
That's how regenerative braking works, huh?
Yes. And this is actually a very cool technology. Does anybody know when the first mass-produced American automobile that had this electromagnetic braking, basically the first electric car that used this, was manufactured in the United States? Does anyone have an idea when we had the first mass-produced electric vehicle using this this generative braking technology?
The Toyota Prius.
You're off by quite a bit. Because the Toyota Prius, that was until what, the 1990s or the 2000s? It was the 2000s, wasn't it? Yeah, that's way off. Who was that?
I don't. Could you type your name in chat, please? Whoever just answered.
Anyone else?
Could it be the electric cars, the trolleys like in San Francisco, those types of vehicles?
Specifically said mass-produced automobile. So the trolleys are not automobiles.
So the first answer was Jacob Harry.
Okay.
And then whoever just answered again, could you type your name in chat?
How about a year? I don't think many people would, it's rather esoteric. I doubt many people would be aware of the actual name of the car company because it's no longer around. But the year was 1905. We actually had mass-produced electric vehicles before the Model T.
Wow.
And once the Model T came out, all those electric car companies, and I think there were at least two big ones, they went out of business because they could not compete. Remember what I said about batteries a while back, 100, 200 years ago? They were rather dangerous. They tended to catch fire and explode and leak acid. The cars did not have a very large range. The electric cars back then could go maybe 10 miles before they need a recharge, and they were quite expensive, significantly more so than anything with an internal combustion engine. So those companies went out of business. But we've had this technology for quite some time. Now, if I were to have more coils on this tube, would that make the magnet go slower, or would it cause any difference at all? Any thoughts?
Well, wouldn't it make it go slower?
Okay, you would think, what if I had solid copper? Would that make it go slower?
Wouldn't that just make it one big one?
Let's see, it's,
Be Horsley?
yes,
And Ms. Scheiss was the second answer.
okay. Well, what I have here is I have some copper pipes. Do we have the camera rigged up to look down them?
We're gonna have to use this one.
Okay, folks, there's a magnet right near the other copper pipe. I'd like you to take turns going to that one and dropping the magnet down the pipe.
Demonstration before.
I've got just a chunk of aluminum here.
Oops, sorry, Dexter.
Are you still getting power? If I drop the aluminum slug down, it goes pretty fast. Drops all the way down. If I drop the magnet, however, folks, come on, stand up, go to the other tube.
This is cool, guys. You don't have to do this.
The magnet for the other tube, yeah. Oh, I think it's gotten, no, it looks okay. There it goes.
Yeah, you want to have the clamp far away from the tube because they have that magnetic attraction through it.
Mhm.
Okay, go ahead and plop it up again. Go ahead and drop it down. And try to keep the magnet away from the laptop, especially the laptop screen.
Yes,
Is- Yeah?
This one is.
Okay, again, you want to make sure that the clamp, which has iron in it, is not near the copper tube.
This direction.
So right when you set these up, you want to make sure that they're set up like that. So go ahead and drop it down. Just there we go, so come on, get a look. I this at a school once
Yeah, I was there.
where I actually did this at many schools. And I remember one student commenting in one of the questions, asking, where did I get the slow motion camera? That's not what's going on. Is that showing up okay on the video for the?
About 15 seconds it takes to drop through.
It's quite noticeable.
Uh-huh.
Okay, everybody in class get a chance to look down the tube as the magnet falls?
It almost seems like the kind of thing you could use to win a bet, that you could
Could
Drop
you grab
it.
the aluminum slab, please?
that you could drop it down the pipe
I
and
need it
then
over
catch
here.
it with the same hand.
Okay, folks, here I have a copper plate. And copper is not magnetic. There's no attraction between the copper and the magnet. But however, if you move the magnet near the copper, just like what's going on in the copper tube, you're going to create electricity in that copper. So just a regular aluminum slug, yeah, it rolls down pretty quick. But the magnet will roll quite slowly because as it moves, it's creating electricity in the copper. That takes energy from its motion, but also what's happening is you're creating electric currents below the magnet where the magnetic field is getting stronger to produce a magnetic field to push the magnet away. And as it rolls down, you're going to create electric currents above the magnet where the magnetic field is getting weaker. That are going to be in the same direction as this magnet to try to pull it back. And if I roll it at an angle, you see it curves. Because there's no metal over here, therefore no currents to pull or push. And then gravity becomes more important. The side of the magnet that's closest to the edge, you'll get more of a push down the incline from gravity that you will on this part of the magnet that's closer to the center of the plate. And so it will naturally curve.
I need that for when I'm bowling.
Yeah, this would be nice to have near the gutters, wouldn't it? Except unless you bowl down an incline,
Yeah.
the ball will come to a stop quite quickly. Remember the whole electromagnetic braking thing. But it's remarkable. In the copper tubes, what's happening is you're having electric currents form above the tube in such a way to pull the magnet up. And below the magnet, you're going to have currents produced in the tube in such a way to apply a magnetic field that's opposing the increasing strength of the magnetic field by the magnet, and that's going to push it back up. And let's see, could I get a volunteer to come down here and feel the force? Someone? One of the three of you, perhaps? Mr. Anderson, I know you've seen this, experienced this. Mr. Horsley, Ms. Muro, Ms. Green. Could one of you come down and feel the force? Come on down. So again, there's not an attraction, but if you move the magnet, you'll feel something. I want you to describe what you feel. Don't touch the plate, have it hold it above,
Okay.
and just try to move it around. You feel anything?
It's like a little resistance moving it left and right.
Okay, the magnetic field is strongest near one of the flat ends, so rotate it so that the flat end is pushing.
Oh, so it feels like it's kind of twisting it in my hand. So the bottom is moving in the direction. So if I move it right, it feels like the bottom wants to go left,
Uh-huh.
and the opposite when I.
That's because the copper to one side of you is trying to push the magnet opposite direction you're moving, while the currents that are forming on the other side, as you're moving it away, are trying to produce a magnetic field to pull it back.
Well, that's cool. Awesome. Wish I said that.
And if you held the magnet still, there was absolutely no attraction. Only if there was motion did you notice something. So this is more of a show and tell device. Maybe you've seen a flashlight like this. Basically, there's a clear coil, the copper coil, and there's one of these big magnets. And, oh, it's on, but it's pretty dim. But if I shake this, when you shake it, you force the magnet to move in and out of the coil. That's basically charging up a capacitor, something that stores electrical energy. And you can see that now this is quite a bit brighter than it was a little bit earlier. And that this is the flashlight that never goes dim. You just have to shake it if you want more light. So, works on the same principle of this generating electricity. Now, I have another device here that is hooked up to alternating current. So this is like a big electromagnet. I got lots and lots of coils here. And when I turn the switch, well, it's producing a magnetic field. But it's producing a magnetic field that changes in direction. Let's see. Ladies, can I get you to come down here? I'm going to pick on you because I have two magnets and Mr. Horsley is already.
You have a
Question, Dr. Steve.
Yes.
Yeah.
Would a device
So,
like the flashlight ever face corrosion
move over
problems? The battery's face?
okay, repeat the question, please.
Would a device like the flashlight ever face corrosion problems like battery's face?
No. The thing with the corrosion problems is you've got basically an acidic paste inside the battery. And if that acid paste ever leaks out, you get the corrosion. So no, you'd never get this thing corroding. You wouldn't have to worry about taking the batteries out if you're not going to use a flashlight in a while. Okay, ladies, I'd like you to hold the magnet in your fist and pretend to be a Scotsman on a horse, if you understand the reference at all. And bring it close to the coil here, and I'm going to turn it on. Closer, closer. Can you feel anything closer?
Yeah, it's vibrating.
It's vibrating. Can you feel that?
Yeah.
Okay, so we can go back in the cups. So it's vibrating. This is producing a magnetic field that's changing direction 60 times a second. That means it's going to pull and push on the magnet in your hands 60 times a second. So Victoria?
Yeah.
And Yadira?
Yeah.
Okay. And so you can feel it pushing and pulling and pushing and pulling. Same sort of influence that was on this filament when we had an alternating current near a magnet. But a changing magnetic field is just like a moving magnet. This will create electricity in anything metal nearby, including the wiring around this box connected to this light bulb. And if I have it suspended upwards, the vibrations from this guy on the table. I was wondering what is vibrating, and that's what it was vibrating. Okay. And in fact, Mr. Anderson, can you help out? I'm going to try to hold this up.
Mhm.
And could you stick your hand underneath between the magnet and there?
Mhm.
Okay, remove your hand. Everybody look at the brightness of the light bulb. Maybe stand to the side so folks can see. See any change in the brightness of the light bulb? Maybe if we have the lights off. Is there any change in the brightness of the light bulb as he moves his hand in and out? I'm not seeing anything. Okay, that's because, again, we are transparent to magnetic field. It does not affect us, our physiology. And so there's no diminishing of the magnetic strength if the magnetic field passes through your flesh. Remember this when people are trying to sell you magnets. It's quackery. There's nothing to it. In fact, there was an incident at the Southeast Idaho Fair where you had this fella selling therapeutic magnets. And to demonstrate how effective his magnets were and how strong they were, he had this magnetic field sensors, basically a Hall effect probe that was hooked up to make a buzzing sound and have lights that would flash. And they'd flash brighter and more often the stronger the magnetic field. And he was using this to show how strong his magnets were, and that they would basically detect something if it was close to between me and Colton, which is about 2 meters. So even, well, actually more like about a meter. It was about a meter distance that you'd start to see a signal, and they get really strong if they were close. And of course, he's got his microphone and speakers set up so that, you know, everybody could hear what he's saying really well. And I said, that's amazing. I can't believe how strong those magnets are. That's incredible. And I'm acting really, really enthusiastic about it. And of course, he loves, people like that love when folks in the audience start to, you know, show enthusiasm. That draws attention. And I had him hold the wand not about a half a meter away from the magnet. And I stepped between them and then stepped away, stepped between them. And I'm going, that's amazing. It even picks up the magnetic field right through my body. In fact, there's no change whatsoever in its strength. That's amazing. It's passing right through me. It must not be affecting me at all. That's incredible. It passes through me and I don't absorb any of it. It can't have any influence on my physiology. That's incredible. He turned off his microphone and told me to go away. But it was very enjoyable for a short period of time. Okay, but we are mostly wet, gushy, salty stuff, a lot of water in our bodies. So this will even work underwater. Magnetic field goes right through the glass, right through the water. This is called an isolation transformer. It is more than meets the eye. But this is how transformers work. You have one coil where you send electricity into it, changes in time, that'll create electricity in another coil that's nearby that will also change in time. This is how we transmit power into hospital rooms, where you have people that are microshock sensitive. Remember talking about the dangers of electricity earlier? Even a microamp of electricity going through the muscle tissue of your heart could send you into ventricular fibrillation. That could lead to death. And if somebody has the high electrical resistance of the skin compromised due to open wounds, catheters, IVs, or some other intrusive probe, they are microshock sensitive. Once the high electrical resistance of the skin is bypassed, you're far more susceptible and at risk from electric shock, causing microamp currents throughout your flesh. And if you get even a microamp going through the muscle tissue of your heart, you're in trouble. So to avoid the possibility of electric shock, so many things in the hospital are designed to avoid static electricity, but also power delivery. Since we use AC power, well, it's very important to have that third grounding plug on pretty much all of our devices, such that the metal casing of the device is connected straight to ground. So if there's some sort of short in the device, the current will go to ground rather than through somebody that touches the casing. That's a precaution. That's why we have that third plug. But for more safety, an isolation transformer is used. With this going on in the water, there is no preferred path to ground. I can stick my fingers in here, even play around in the water. If this is big enough, I could even take a swim and I would not be at risk, because the only electricity would be flowing through the wires. And if there was a path to ground through me, that would not matter. So this is a very safe way of delivering electricity to avoid the microshock problem with patients. This is also how electricity is delivered through watertight bulkheads in ships, in that ships are compartmentalized, so that if one section floods, they're isolated from other sections. But how do you deliver power through multiple sections without having wiring go through the bulkheads where you could possibly have leaks? Well, this is the answer. You have isolation transformers that transmit wall through a bulkhead from one part of the ship to another. So you don't have any sort of connection where you could have leakage.
That's another cool use for magnets.
So let's see.
You have a question from Ms. Scheiss. Can you
Yes.
briefly explain how an MRI works?
Okay, a magnetic resonance and nuclear magnetic resonance imaging. What happens is, we talked about resonance, and if you apply a influence to something at just the right frequency, you'll tend to get larger amplitude oscillations. It's like pushing at a kid on a swing at just the right rate. Well, the nuclei, almost all nuclei, all nuclei of all atoms have a magnetic moment or a weak magnet. And if you apply a time-changing magnetic field, they will tend to vibrate or oscillate. This does not affect the chemistry of the body any at all because it's the nucleus. It's only the outermost electrons that actually interact chemically with anything, so you're not changing anything chemically. But if you send a signal in, it'll tend to resonate. If you send it at the right frequency, it'll tend to resonate with those atoms. So in MRI, what we do is we focus on the most common atom in the body, which is hydrogen. And we send pulses in, very narrow, very directional, very precise, that will then probe to see how much hydrogen is along that beam path in the body. And in tissues, you're going to have different fractions of hydrogen. And by seeing how much energy of the beam is absorbed, you know how much hydrogen was present along that beam. And by changing the angle of the beam and its direction throughout the body, you essentially map out the hydrogen concentration in the human body, which will image the tissue, because different tissues have different ratios of the hydrogen. So that's how nuclear magnetic resonance imaging works, except they dropped the word nuclear because that made people scared. So it's now just called magnetic resonance imaging. Okay, so let's, remember I said that this will produce a magnetic field that changes in time and it'll create electricity in anything nearby? It'll do that including in a ring. So that'll create electricity in this ring, but that electricity switches direction 60 times a second. Basically, if current arises in this ring, it'll become a magnet. One magnet on top of another magnet. What do you think might happen? Any thoughts? Was that Ms. Scheist that had that question? Is that right?
Yes.
Okay. Any thoughts of what would happen if I turn this on with that ring nearby? If that ring becomes a magnet, what might happen?
Gonna be attracted,
Actually, it's kind of repelled.
or that.
So one or the other. And I've got something similar here. Where here, the magnetic field quickly drops off away. It's not very strong right up here. But here, the magnetic field is in fact strongest up about here. And so you can see that we have a repulsion. Now, it's an average repulsion. In the 60 times a second, the current is switching direction. And you think that whenever the current is increasing in strength, we would have a repulsion. And if the current is ever decreasing in strength, we'd have an attraction. Well, we do, but there is a phase shift due to the time lag in the magnetization of the iron that's in here and the current, and also a time lag between, it takes a while for the charges to slow down and switch direction. So because of those, what we call phase shifts, the net average is an average repulsion. But in general, we get repulsion in each case. So here's, oh, do I have? I think we're going to get back to this because there's one other demonstration I really want to get to before we're done. And because I could take a bit longer on this. But back to our speaker. If I send the output of Braden's phone into this electromagnet, I will get a time-changing magnetic field. Now, what I have here, does this still have the batteries in it?
It might.
Okay, let's take that off then. Let's check. Yeah, it does work. Okay, so this is an ingenious device, a cassette deck tape recorder player. Has anyone seen something like this? Okay, the way these work is you would have these little boxes called cassettes that inside would be two spools that would have a magnetized tape. So it's called a tape deck for that reason. And those are called tape cassettes. And you have little spools of this tape inside that was magnetized along the length of the tape. And when you hit play, a motor would spin this tape past a little pickup coil. If you open it up, you would see right here where my finger is, I don't know if that shows up well, a little teeny coil of wire attached to what's called the pickup head. And as the magnetic tape moved past that coil, it would create electricity in that coil. And as the magnetism along the tape changed, well, the frequency of the currents produced in that coil would change. And those currents were then amplified and sent to the speaker to produce music. Okay, actually an ingenious device. But when you hit record, what happens then is the speaker is then turned into a microphone. Just like a motor is a generator, a speaker is also a microphone. So if you speak into a box like this, you'll feel it vibrate. And if you happen to have a magnet nearby, that vibrating coil moving near the magnet will create electricity at the frequency of the vibration. So a speaker is really the same thing as a microphone, just as a motor is the same thing as a generator. So the speaker on this will act as a microphone, and then the signal from that microphone will then go into that coil and magnetize the tape as it goes by. Is that cool? An ingenious device. So it could record music as well as play it back. But it all relies on a magnetic field, a changing magnetic field being picked up by that coil. There is no tape in here, and I've got it on play. And let's turn the volume up. So there's no tape nearby, but I can create a time-changing magnetic field with a tape, of course, moving in there, or with this electromagnet. Go ahead and hit play. Is it playing? Yep. Okay. Is that cool? Okay, so essentially what I produced here is this is now a radio antenna. This is a radio broadcast antenna. It's producing a time-changing magnetic field that in turn creates a time-changing electric field that will then induce a time-changing electric field. Did I say that right? Anyway, that disturbance will propagate out at the speed of light. Basically, if you look in the radio colors, this is a pulsating, glowing piece of wire because it's producing radio waves. The range of our perception in color is limited to what we call the visible range. It's a very small range of what we call the electromagnetic spectrum. But a lot of the light that's out there, especially when we look up into the night sky, is radio frequencies, radio colors. And so this would actually be a very pretty pulsating light source if you could see into the radio colors. But that light is actually, when it hits the coils over here, it's creating electricity in those coils at the same frequency as the changing magnetic field, as the same frequency as the currents that are going into this coil. So, pretty cool. I created my own radio station. Now, actually, I don't think we have time to get into this. What I was going to do is talk about what type of coil. I've got a wide variety that can work better. And I could just do like this one. Remember how this one went all the way, almost all the way to the ceiling? This coil is actually has a smaller inner diameter. So it's going to be closer to this coil. The interaction is a bit stronger. This one is really, really small. Its cross section is a lot smaller. Remember we talked about electricity being like water flowing through a pipe? Well, this is like a nice big thick pipe. This is like a very narrow pipe. Which do you think will conduct electricity better? A thick pipe or a thin pipe? A thick one. Same thing with water. Yeah. That's not working as well. Okay. How about a ring like this?
Oh, that one's good. Doesn't form a complete ring, it's got a slit in it and
Nothing. This one doesn't work at all because there, is that showing up okay?
Yeah.
There is a slit. Electricity cannot flow all the way around because of this slit that's cut. There's a gap. We can't have electricity going around, so we don't get the currents created in it. That's really about all the time we have. Thank you for your attention. We'll then move on to a lighter subject tomorrow.
I remembered something funny in middle school. One of my teachers had a cassette tape and a pencil, and he asked whether they had to deal with one another. And they just said, you can use the pencil to rewind the cassette tape. And he said,